Hi everyone. So welcome to today's live stream. Hope everyone's well and doing okay. Got us a bit of a special one for us today. We've got Alex here from he's in my team, which is the process specialist team, but he's a robot specialist. So he's been working with robots pretty much since he could walk, and yeah, we got him on today to talk about how we control robots from Fusion. So again, like normal, everyone, please be as interactive as you can in the chat. I'll try and answer questions as quick as we can, and let us know if there's any audio or video problems, and we'll do our best to sort those out as we go as well. So again, for those of you who don't know me, my name is Richard Stubley. I'm one of the process specialists based out of Birmingham, UK. Done metrology and machining and manufacturing since I can remember. So, go on, Alex, do you want to just let people know who you are and what you do with us?
Hi everyone, I'm Alex. I'm based in Portugal. As Richard said, Richard is quite kind. I've only been working in robotics for about 12, 13 years, I think. All I've done, similar background to Richard, started doing CAD/CAM work. So a lot of metrology, a lot of reverse engineering, some 3D printing at the time, and then eventually brought me to CAM, and more specifically CAM with robotics. So the only the only CAM I've ever done is with robotics. So my expertise is the same as Richard, CAD/CAM, but I would say more on these specific machines. And what we'll show you today, or hopefully share with you today, is we've developed 2 posts. We want to enable people that have robots and have Fusion to play with robots and maybe start milling with robots. Walk you through the steps, understand the basics of the post. And the reason why we did it is, personally, I think robots are amazing machines to start off, to enable people with an easy access machine, easy to learn machine to start printing, 3D printing, or other type of applications. So milling is one of them, and this is what we're focusing on today.
Yes, that's good. So again, everyone, this is really going to be very useful for anyone out there that's got a robot and wants to, maybe use Fusion to control it, to do subtractive toolpaths. Anyone that is thinking about potentially the uses of what they could do, with a robot. We've got someone here from rainy Birmingham as well. I can sympathise with that looking out at the moment. So yeah, so anyone that's thinking about using a robot for doing subtractive toolpaths on their components. We've got William CG on the line as well with a big smiley face. So credit to Will CG. Some of the videos have been done by him. So he's another Autodesk employee out there. Thanks everyone for watching. And yeah, so we're pretty much up now with the timer. So let's get cracking on this. Again, let us know if there's any problems, audio, video, and we'll do our best to sort those out. So for anyone that's ever been to the Birmingham Tech Centre, or anyone that sort of wants to know a bit more about what we're about, we've got just basically YouTube Autodesk Birmingham Technology Centre, and you'll see a nice showreel video about what we do there. But this is particularly our robot cell. So Alex, do you want to just give us a rundown about the robots and what we can do with them?
Yep. So we have actually 2 robot cells. So this is one of them. This is one that Will is manning. He's the one who's responsible for running jobs and helping us test all these things on this specific cell. So again, thanks Will for helping us out, getting all the comments for this video. We have 2 KUKA robots. They are KR210s. We have a fixed table, as you can see. We have an external axis position with 2 external axes, which means we have a tilt and a rotation axis. That's the DKP400. KRC4 controller. And we have a lot of kit on here. So we have a vacuum table for our fixed table. We have a heated bed for 3D printing. We have each robot has a tool rack with 8 tools. So you can actually see just behind me, we have a few tools. Actually, we have a probing device on there as well. And then behind Richard, we have actual end effector changing. So our robots are kitted with end effector changers. That means we can change the whole end effector. So it is quite the toy. We are behind Richard. We have a hot wire cutter, which is right at the back. We have a chainsaw, which is that red. The guard of the chainsaw is that red thing that you can see over there. And we have a gripper, and that is, and obviously we have spindles on each of these machines. And above me on the robot on the right-hand side of the screen, we have a ambit HMT polymer extrusion system. So it's 3D printing. It uses pellets. We have a drying system, and we have all this kit to be used really on this cell.
It's
pretty cool stuff.
So it's quite interesting. So robots basically are just a universal piece of kit from the base, their mounting point, to the end effector, and it's just literally the end effector that converts them into whatever they're going to be doing, isn't it?
Yep, and that's the for me the whole interest of driving robots and learning how to use machines is it's quite a versatile machine. Changing the end effector, you can do different operations. So in the same machine, you can mill, you can add material, you can pick and place. So it is something that is quite useful for the future of manufacturing. I would say it can be an amazing machine if you know how to if you control the machine via fusion, for example.
Yeah, that's good. So this is an overview of the cell that we've got in Birmingham, but sort of this is a few pictures that Alex has sort of brought together to sort of show sort of what some of the common robot types are. So what we've got here is just some examples of, basically a handheld router, isn't it, Alex? Really, that's just been bolted onto the robot.
Yep. So this is one of the cells, one of the many cells that we have also in our technology center in Boston. So thanks, Steph, for helping us out with testing and also providing some data for this and videos for this presentation, for this video. The reality is this is what got me into robotics. So the other cell that we saw previously is like the high-end, full-spec solution, all the toys. This is what got me into robotics. Is a handheld router. You put a tool on there, you find a way to fix a spindle or a router to the robot, and off you go. You're learning robotics. You're playing with a CAD CAM tool and getting your robot to do stuff. And so I love this type of approach as well because it means it's accessible to a lot more people. And I think this is an ARB 1200 IRC5 controller, and as we said, a DeWalt router mounted as a spindle.
Yeah, I suppose because at the end of the day, if the router is good enough to machine the wood when it's held by a person, then it's powerful enough to machine wood held by a robot. I suppose there's no difference then, is there, in the output power of the actual device? Doesn't matter if it's a person holding it or the robot holding it.
Yeah, and also if we focus on what type of materials people are processing with subtractive technology in around using robotics, it's never going to be the metallic materials. It's always going to be non-metallic. So foam, composites, wood, tooling board, all those type of things, EPS, foam. So there's so many applications that you can use a robot. The precision of the machine will be enough. The type of materials that you're going to be processing are going to be okay with it. So a lot of people don't like to mill EPS or PU foam inside a machine tool because it's going to be all that material is going to be stuck onto your encoders and everywhere in the machine. So these machines are much more appropriate for these type of applications, I would say.
That's good. Cool. So hopefully people out there got a good understanding of robots, but what we just want to quickly show is how you'd actually apply toolpaths inside of Fusion to then actually make those robots move with. So there was a video done by one of our colleagues, Dave, about 2 weeks ago called Introduction to CAM Machining. I think we also called it My First Toolpath in the description. But I'm just going to very, very quickly go over the toolpaths we see on the screen and just how we quickly made them, just so everyone's got a rough awareness. So if you have got a robot, sitting in your garage at home or doing nothing, you can hopefully then go to your robot, go to Fusion, and look at creating some really just simple toolpaths to make the part. So this is what we've got here. We've got a facing toolpath just to go across the top. This was what was the material, Alex, that we used? Was it resin? Was it model board?
I think it was PU foam.
PU foam, yeah. But again, I wasn't machining it, but I did see it, and it was pretty rough when it first went on the machine. We might have got away without doing the facing pass on top, but it's just good practice really to always face your material off, especially when it's been rough saw cut. Maybe we use the chainsaw to actually cut the blocks up from the stock before. So yeah, we've got a basic facing toolpath on here. We then do what we call a roughing toolpath. So really heavy cuts, not very much definition, but let's get rid of as much material as quickly as we can. That's what roughing is. We've then got a finishing cut, which we're using a ball-nosed tool. So effectively, the tool's got a complete radius on the end as a ball, and that's really nice for finishing because it can create nice curved surfaces. I was worried about the chat today, but now Frank's online. Actually, he's going to be my chat man for the day. So cheers for answering some of the questions about robot rigidity, Frank. You've got a job for the next half an hour. And then we've got a contour path here as well, just to finish off these side walls. So let's quickly have a look at how we did these toolpaths. So the brilliant thing about Fusion is with minimal input, you're hopefully going to get a toolpath out of it. So I'm just going to click face up here. I need to choose my tool, and I'm just going to quickly make a tool as well. So let's select the project I'm working in. I'm going to click the big plus symbol to make a tool, and I want to make a flat end mill. So I'm going to make a flat end mill. So I'm going to go 16mm end mill. Helps if I put the eye in. And then just choose my cutter geometry. So the diameter is 10mm. The overall length, so what I'm probably going to do is make this a little bit bigger. So let's go for like a 200mm overall length. Let's go 150mm below. Then that's going to probably be 125, and then a 100 flute length. So you can see very quickly we can build up our cutters. So again, if you've got your robots at the moment, you're going to want to just roughly build up your tools in Fusion. We can start doing holders next, but we're not going to cover that in this session. An important one as well is this post-processor tab. So we need to tell it what tool the robot's going to think it is. So of course we've got 8 tools in our robot tool changer. We need to choose the correct number so the robot knows what tool it has to pick up, and then also the geometry of that tool as well. So yeah, so I think I'm going to go for tool 2. Why not? Just going to accept that now and then select that tool. So you can see I've got my tool here. Got that 10mm tool. And then in my passes tab. So there's a couple of things that I wanted to talk about. Pass extension. Basically, it's really good practice to never cut exactly the same size as the stock, because stock can vary a little bit. So I'm just saying, let's just go 30mm over on my passes, and then just add an extra 3mm onto my stock as well. So that's hopefully going to, just give us a bit of wiggle room, if we've got a slightly poor cut stock. And then the step over is effectively how far the tool's going to move each time it passes over the part. So that's really going to be defined on how powerful your robot is and how powerful the end effector is. If your spindle's going to be struggling, or the physical axes of the robot's going to be struggling, you might want to reduce that to reduce the load on the tool. Hit OK, and I get a toolpath. So all I've literally done is selected my tool, hit OK, and I've got a toolpath. So again, we're not going to go over much more than that in this one. Please watch Dave's live stream for a couple of weeks back. And I'm sure you'll find lots more videos on sort of how to make toolpaths inside of Fusion. But we can see there roughly how we built this up. We've got all these toolpaths here that go down, and then we can also just quickly simulate as well. And we can see as we start machining the fact it's cutting away on there. So we've got the roughing toolpath, then we're going over the finishing, we've got the contour. So that's how we've ended up with our finished part. So yeah, so again, really quick example of it. I'm not going to go too much more into it than that. Please watch a lot of the other videos. We're going to go on there. Thankfully, Frank and Stephanie are taking really good care of the chat for us now. Talking about, just using different sizes of robots and the pluses and minuses versus strengths. So thanks very much.
Richard, can you also show us how to do the detail of the setup, the WCS number?
Oh, the setup, yeah, very good point. I can't believe I forgot that.
You haven't forgotten.
No, I was just waiting for you to remind me, Alex. So what we've got here, we always start with a setup. And a setup is where we effectively just define some basic parameters of what's going on. So the first thing we define is our operation type. We're doing milling. If we're doing turning, we could do that, or additive. The next one is the direction of our Z. So this will be really important later. And, hopefully we'll show some videos and they'll make all these clear why this Z direction and the X and Y is so important. We've then got our origin point. So that point there, of course, this is an absolute coordinate system, not an incremental coordinate system. So all the 0 coordinates are going to come from there. The next thing we're going to look at then is our stock. So what's the size of the material we're going to be machining this out of? So we can effectively set the stock up here, set the size of that up. If you're not quite sure about your size of stock, it's always best to go a little bit over rather than under. And then finally in the post-processor tab, we've got our WCS offset number. So anyone that's ever used a milling machine will think of this as sort of like G54, G55 numbers. We'll cover this later, what this means on robots. But all we need to make sure is this value here matches up with what we've set on our robot. So again, we've got some videos on why that's important and what we need to do. So that's really important on there. So yeah, do you think I've covered everything on that, Alex, or do you think I've missed anything important?
Yeah, so WCS and tool number is two big things for us.
Yeah, perfect. So just to prove that, we're not just saying things that we think, we actually have done this. This is the video of that part on our robot in Fusion. There's a very handsome guy about to walk past in the background any second now. There we go, hopefully you recognised him. So that's of course just doing the roughing passes now on our part, those 2D adaptive roughing passes. Just some different angles so you can see what's actually going on. This is slightly sped up. We like to make things a little bit easier and make sure we don't break anything on our first runs normally. So yes, that's just going on there, doing these 2D adaptive going all the way around. And then we'll do that parallel pass afterwards, just to put that form over the top of the part. So that's what we've got there, really. Would you say sort of parallel toolpaths are sort of the most common for the finishing with the robot, so you can sort of keep a nice linear motion going across the part?
Yeah.
There we go.
Yeah, we tend to do that. Yeah.
Cool. Okay, so basically Alex has got this. So this is basically a little overview of the workflow, really. So do you want to say what you've got here in these 6 boxes?
Yeah, I think it's hopefully the pictures tell the story, but just to make sure that everyone realizes that we created the subtractive toolpaths inside Fusion. We don't actually show the post-processing, but we post-process the files. You get the files from your PC either via network or via USB stick. Load them onto your machine, provided the output workplane WCS is correct and the tool is correctly defined. You run that job on the robot, and you get a milled part, as you can see there. So this is very simple diagram or steps of the workflow of how to use your post-processor to run the job on your machine.
Yeah. So we're going to mention post-process quite a few times, but for anyone that sort of doesn't know what post-processing is, if you've basically just been doing pick and place with your robots before, what you've got to think about is you've got all those blue, green and yellow lines in Fusion, but how on earth do we go from those lines to, NC code? Is it called NC code, Alex, for a robot still?
Robotics. Actually, that's a very good point. There's no standard of a language for robotics. So each manufacturer would have their own language. So the post output is specific to each robot manufacturer.
Okay.
So we're gonna. So the posts that we created are KUKA and ABB. So they have slightly different names for the same thing, and they have slightly different syntax. They all do the same thing, which is drive the tool to a specific position, a Cartesian position, relative to that coordinate system you define on the part. So provided that the coordinate system defined on the robot matches what you've defined in Fusion, the robot will go to that position. So they have their own language name, and the syntax is slightly different, but they all do the same thing, basically.
Perfect. So basically, the post processor is going from those toolpaths we see in Fusion to the code that your machine can read in its correct language. So if you've got an ABB robot and a KUKA robot next to one another, they'll both have a different post processor because they'll both speak a slightly different language. So that's why it's really important to make sure that you've got the right post for your robot and we're going to go over in a minute some of the key points that we think you're going to need to know, to run your first toolpaths really. So yeah, so that was a little bit about it here. If people weren't too sure about what are post processors, we're going to keep mentioning this word post processing, but what are they really? So this is another quick workflow that Alex has got.
Yes. So the previous workflow we saw was very common to many Fusion users. This one here is also common to a lot of Fusion users. So it's basically using third-party software to validate your code. So whatever comes out from the post processor, you can import into either Robot Studio or KUKA Sim, which are the two softwares for simulation from manufacturers, and you can validate your toolpaths. So any issues, any access limits, any orientations of the robot that don't look correct, you can validate these before you run your job on your machine. So very similar to what people do with third-party software, for a machine tool as well.
So what sort of simulation packages are you normally using to simulate your toolpaths?
Well, that's a good question. In the past, never used any. So when I started robotics, either I didn't have access to one, or I just didn't bother with it. The reality is, what if the work plane on the part and the tool that you're driving are correctly defined and matching what you should have inside the software, everything should be fine. Obviously, if you're doing complex jobs, the third-party software does a good job. Luckily, in previous software I used, we had a validation via simulation inside the software. But so this is just a pointer saying that, yeah, you can, even without simulation inside Fusion, you can still run these files that we generate into third-party software for validation.
Oh, I get what you mean. Yeah, so you could either, this validation process is optional. You haven't got to do it.
Yeah.
No, that's interesting.
Recommended, but if you don't have it, you can still play with your robot. You can still get away with it using the post.
I suppose it's the same as milling, really, isn't it? You can buy third-party packages to simulate the NC code for milling, or if you trust what's coming out, then you can run it. So it's just it's good for people to realise that it's not a a mandatory process, this validation.
Yeah.
So what we've got here is post options. So there's a big one here that, we've got these options in the post, and there are some that are really critical that you might not need to change, but it's going to be really fundamental that you understand what they do and make sure that it's correct for your configuration and setup of your robot cell, really. So where do you get these posts from? We keep talking about posts and post-processing, but what are they? Where do you get them? So if anyone's done milling, you'll know that Fusion gets installed with a subset of post processors, but we don't want to clog up everyone's C drive with the hundreds and thousands of posts that we've got on. So what you can do is go to cam.autodesk.com/HSM posts. What you do here is search for either ABB and KUKA, and you'll see the post processor that you can download, and then you'll also see a PDF that our experts like Alex have spent a lot of time writing and making some real fundamental information that you guys can sit down, look through, and make sure that you're all set up. So yeah, and then make sure you save this somewhere locally, and then you can reference that inside of Fusion. So if I just go back up to here, what you can see is you've basically got your configuration folder at the top section there with the ... You click on the ... and you navigate to your post processor, and you can see in the post configuration that next blue category down you've got KUKA Robotics KRL KUKA_Rev3. That will be your post processor. So you can see that you just make sure to put them in the right place, and then of course you can you can make sure you choose the right post processor from there, really. So that's how to get them and go on that. But again, I don't want to go too much into the post processing side. We've got a lot to cover today. What you can do is watch some of the more milling ones that will really go into a lot of the post processor stuff, and we'll also let you know how to get in contact with us after this. So I know absolutely nothing about robotics. So what I said to Alex is, imagine you're teaching someone who has no idea like me, and you've set the bar low enough then for anyone else. So what he came up with is his robot checklist. What are the most important things that Alex does before he actually runs anything on the machine? So do you want to go through these and just give us a brief overview, and then we'll hit the deep dive slides after this?
Yep. But luckily, and if all goes well, we have a few videos to accompany this description. So, like on a machine tool, when you get on a machine tool, you know how to, drive a tool. You know what is a positive Z direction, negative Z direction, etc. On a robot, it's a bit more hectic, I would say, because there's a lot of freedom. So a tool is not always defined with the orientation that you would expect for milling. So the first thing that I do is I check the tool orientation and check that the TCP, or the tool center point, is configured correctly. So that's one of the things that I'll hopefully explain to you with the help of Richard and a few videos. The other thing is a simpler one to understand is we need to define a coordinate system on the part in order to tell the machine where that part is located. Also, in Fusion, we post-process from the same location. So very similar to how you run a job on a machine tool. The last one, slightly harder to explain, and hopefully we'll try not complicate things too much, but just give you an idea of how robot configuration is important and how we can set it in this post, and how to read the robot axis position and input it into the post-processor option as well. That will give us some help in getting a good result.
Perfect, Alex. So I'm just answering a couple of the questions here. We've got some really nice comments from people enjoying the live stream so far. So yeah, perfect. So
that's good to know.
What we've got here, we're now going to talk about. So is this RTCP or TCP? Because I get them.
TCP.
TCP. And what's that? Tool center point.
Yeah.
So, cool.
So basically, in this case, it's not a tool; it's a spike. So we use spikes on our cells to measure positions or measure a coordinate system. It's a bit more precise than using a tool. But the theory is the same. So if you place your tool against a static spike or another tool, and you pivot around the tip of the tool, just double checking that it's calibrated correctly. So what you see now is the tool is not moving away from the other static tip, so the pivot point is good. If it was bad, it would be moving into the
So rather than being matched up, they'd start moving away as it rotated like that, rather than staying in the same place and actually pivoting perfectly.
Yeah,
it would start moving away from it.
So this is a basic test, I would say. What you can do is make sure that you select the tool that you want to drive or you want to mill with. Do this, make sure the controller knows what tool you selected, and you select the coordinate system of the tool, because there's a few coordinate systems in robots. So make sure it's the tool coordinate system, make sure the tool is the right number. Do this test and you know if it's correctly calibrated or not. So this is figuring out if the tool tip is correct. Most important for multi-axis jobs, not so much important for a 3-axis job.
Cool. But yeah, one thing I do want to say is this is actually nothing to do with Fusion, is it? This is just making sure your robot is set up and running correctly.
Yeah.
So the next one is flip tool frame. So I'm still learning this, so I'm definitely handing this one over to you.
I think we missed the video.
Sorry, yeah, we did. Good point. Sorry. Checking the tool orientation.
Yeah. So when you check a tool, you check TCP and you also check the orientation. So thanks for moving out of the way. So what is happening on the teach pendant is my colleague Will is driving the tool. So we've selected the tool and selected the tool coordinate system. That's really important. We're driving it in the positive and the negative direction. And what you can see is we're clearly looking and realizing that the x-axis is going along the length of the robot, and the z-axis is going across the xy, or the base of the robot. So normal to that. And what that indicates to us is that we have a coordinate system at the tip of the tool that has this orientation that you can see on the screen now.
So are we making sure that matches what we had in Fusion?
Exactly.
Okay, so what we had when our setup was in Fusion with the X, Y, and Z, we're making sure that the axes and the direction of those axes match up with what our robot's set up to do. Is that right?
Yeah. So basically, if you go to the next slide, and we can see the post option. Yeah, here we go. So one of the post options, and this is why we cover this, because one, you can confirm the tool is calibrated correctly. Second, you confirm what is the tool orientation, because currently we support 2 tool orientations. The flip tool frame no is the actual setup I had on that KUKA in our facility, so that's why I selected this option. So I asked my colleague Will, so where's the tool orientation? Can you show me? He showed me, and this is what I selected. So for Z plus going up and X positive going in front, I have to select flip tool frame no. If it's reversed, as in Z pointing downwards and X positive pointing back towards the robot, so flip this around the Y-axis 180, it'll be flip tool frame, yes. But this is all in the documentation, so
Okay,
this is just a little pointer on how to check these things on the actual machine.
Yeah. Cool. So now look at actually setting the WCS. So what are we using here, and why are we doing it?
Question. So everything we do in robotics in terms of this type of jobs, we're doing a relative job, relative to a coordinate system. So what we're doing is defining this coordinate system on the part. So previously we defined or we calibrated our tool, or we confirmed the tool is a known length. And what we're doing here is we're measuring 3 points. So the first point was the origin. Second point was on the other side of that edge. That defines a line. And the third point is on the XY plane. And this defines a coordinate system on the corner of that block, which is what we intended. Because if you remember from Fusion, we defined the coordinate system in the same way.
That's interesting, because I come from a metrology background, anyone out there that knows me, and we have a thing called a PLP alignment, which stands for plane, line, point. And this looks exactly the same. So you've got a point being the 0, 0, 0 coordinate system, the line, which is normally your X, it doesn't need to, but it's normally your X, and then your plane gives you effectively the axis of the Z then. So you can constrain all of those 6 degrees of freedom, X, Y, Z, A, B, C, with 3 features, plane, line, points. This looks exactly the same to me.
So obviously when we post-process from Fusion, we're going to post-process from the corner, the WCS we selected, provided you define the name like you showed us, the number. You post-process and all our coordinates will be relative to that position there that we define on the machine. So I think it's kind of, I think we have a few more videos, but it's kind of the most important things are defined. So how to define a coordinate system on the machine and how to make sure your tool is in the right alignment that you need.
So what we're looking at here then?
This one here, we have just a display of the teach pendant. So most robots can have this option. We're looking at the robot configuration. So if you go to view current position, you can see the position in Cartesian point location of the TCP, and you can also switch from Cartesian to axis. So this is the position of the robot with each individual axis in degrees. And the reason why it's useful is going to be clear in the next few moments, is you can define the starting position of the robot. At least we allow it in our post to be absolute angle degrees or Cartesian position, and you have to use states in turn in this case, or robot configuration. So it's just a tool for you to make your job easier, to place your robot at the start and keep the robot in the correct position during the milling.
Okay, that's good. I suppose this is why it's so important then.
Yeah. So first point, using joints is our default option. I would recommend to use this one. As you mentioned before, Richard, when I started, I didn't have a third-party software to check my simulation of a job. So what I would do is I would manually jog. So after I've defined my tool, after I define my coordinate system on the actual block that I'm going to mill, I will actually jog my robot over the part to see if my robot has any reach issues, if it reaches any axis limits. I can also check orientation of the tool if it's multi-axis, see if any cables get in between. Most importantly, we can define the start posture of the robot by using the joints. So this is why I mentioned that you can read the joints from the teach pendant, input it into this menu here, and when you press post-process, that is the robot posture that you go to at the start of the job. It's very, very useful.
Okay, I'm pretty sure I've got you in. So is this your sort of the one you'd prefer to use?
Yep. This one has no ambiguity. There's only one unique robot posture defined by a series of angles. Whereas if you, on the next slide, we'll see if you want to drive it using Cartesians, you have to add a bit more information. Not always so easy to understand, but we'll try and make it clear for everyone. Yep, here we go. So if I say first point using joints no, which people can, the robot will go to the first toolpath point, and because robots have 6 degrees of freedom, so 6 axes, and the reality is if you're driving a 3-axis toolpath or even a 5-axis toolpath, you don't need that number of axes. The robot can have a slightly different posture than you anticipated. So it's a good idea to define the robot configuration, so what you can see on the screen there. So again, you can drive the robot to the posture you want, the position you want, read status and turn, input that into your post-processor options, and then post-process and run that job. And the next slide will show you exactly why it's important. I think we were discussing this earlier, Richard, and you agree that this does a good job of explaining
it was.
the exact issue that we might face.
I wasn't, you were saying about all the, use joints or don't use joints, and I wasn't too sure. But then when you showed me this slide, I really got it. So I'll try and explain this one, and I'll see if I can. So basically, what we've got here is exactly the same Cartesian endpoint being milled or drilled by that tool, but 2 different solutions that the robot's taken. The big one for me is if you look at A1, so axis 1, the main one where it's bolted down to the floor, we're at 0 and 180, and then you start working the way up the robot, and you see how it's like it's backed upon itself, and you look at the cables, they look all stretched. It doesn't look comfortable. If you were trying to imagine if you're trying to write with a pen, and then you had your arm twisted the other way around. That's to me sort of what it looks and feels a bit like. Is that you've got yourself wrapped up in a twist. I suppose that's what this is all trying to do. Is if you define joints, you can make sure that it's not in this wrapped up scenario. But of course, if you don't, then you risk the robot choosing the wrong solution. How was that for an explanation then, Alex?
It was pretty close. I would just add that if you go for a joint, you define your joints, robot goes to that posture, starts milling, job done. If you go for a Cartesian position and you define an incorrect status and turn, or leave it as default, it might be the wrong status and turn, and this is what you might end up with. So just be cautious with that, and if you want to use Cartesian position as your start, I would advise you to get simulation software to make sure. But yeah, it's pretty close to what you said, Richard. You can have crazy results if you don't have your status and turn correctly for a Cartesian point first move. Hopefully that makes sense.
So we now have a look at robot head angle. So yeah, this is quite an interesting.
So this is an optional one. Yeah, it's my favorite one, to be honest. This allows us to have a bit more control over the actual milling. So what you'll see is the option allows you to add an angle, and what you can see on the screen is we're doing a small rectangle around that block, and the spindle is rotated by 15 degrees around the two axes. What this means is there's an angle on the head on the robot. So in between axis 4 and 5 and 6, 4 and 6, there's no alignment. So I think if you change slide, Richard, you'll see a bit better visualization of this. So basically, this will allow us to have more control and also avoid singularities of the wrist, which is basically what we have. So if I duck down, you'll see head angle 0, head angle 15, and head angle 30. So this gives us, again, the option of avoiding singularities of the wrist, which are the most common when you're milling.
So would you say that having it at 0 is where you're going to get the singularities, but even putting a 15 degree on is going to reduce that risk of singularities?
All depends on where you're milling, where your part is located, because if you think of aligning axis 4 and axis 6, it is basically if the robot is milling right in front of itself. So because the part is slightly below, you won't have that issue. So all things considering, I would always put an angle of at least 15 degrees to be sure.
Just remove that risk of those singularities then.
Yep.
Cool. And I can take this one. I know this one. So before, when I was showing you Fusion, you might have seen the WCS origin that I was doing. So what that basically is doing is saying that you want coordinate system number 1. So again, I'm a FANUC machine tool man, so I think of G54 to 59. But on the robots, you might have seen that back in the second or third slide we looked at, where we had 2 build zones or 2 beds. We had the positioner with 2 axes, and we had the static bed as well. We might have different presets for fixtures on places. So we could have the center of that positioner as 1, and we might have the front left hand of the static one as 2, or the center as 3. And we just need to make sure that whatever we've got our parts set up as, we make sure we have exactly the same one here. So of course that's when we're going to start to have problems, if we have different WCS offsets set to then what the base is set to. So we've got, so as you say, these had to have different names for different manufacturers.
Yeah, the theory is the same though. If you have a KUKA, they call it a base. If it's an ABB, they call it a work object. Others call it user frames. All it is a coordinate system on the part. So what you can see on the first picture is there's a number on the post-processed file. The base data is 1. So if you define your WCS offset as 1, you're making sure that your base data is number 1. So provided you define your coordinate system on the part with base 1 or 2, here you would have to define it with the same number in the setup post-processor tab, and that's what you get on your end result as well in the post-process file.
Perfect. And then, so finally, we're just reiterating how important this tool number is. So we looked at this back at the very start, but just want to stress that whatever tool number you put in Fusion gets passed through the post-processor and given to that robot. So of course, if you had defined a 60mm MMIL, but you actually picked up the 2mm MMIL, of course you're going to inevitably snap it. You need to make sure that whatever you define in Fusion, the numbers then match up with those numbers you've got actually getting output into the code.
Yep. So I'd say this is like 90% of my job, is defining a tool correctly, defining a coordinate system on the part, on the machine. People, having the knowledge like we just showed now to confirm these and define these, and then making sure that when you post-process everything matches. That's like 9% of the work done. These are all the errors that you might get. So I think this is why we chose this format, and hopefully to empower people and share a bit of knowledge, and people start milling with robots.
Yeah, I suppose when you look at it, sort of 2% of this has been Fusion, the rest of it has been just general robot best practices, I think we're going to say, isn't it? Just to make sure that you're happy with how your robot's set up, you're aware of the different options in the post-processor, and you just know how what these options mean, and hopefully give you an insight in what's there. But I imagine the documents you've got go into a lot more detail, don't they, into really going down into the fine detail of those options and what you need to set.
Yeah, but the reason why we chose this format is I think people might not know how a base or coordinate system is defined on a robot. Now they know. Even if they don't know how to do it, they can ask an integrator or ask someone that can teach them, and they'll be on their way to mill with robots, hopefully.
No, that sounds absolutely perfect. So yeah, I think that's pretty much what we're going to have. We're just going to wrap it there. So thanks to everyone for joining us today. It's a bit of a different one, it's less milling machine, still milling, but not a milling machine. But we've got one in the background there for you, just so we all feel at home. But yeah, thanks very much for Alex for doing all the preparation for this. What we're going to do is we'll do a forum post, and we'll put that in the description. So everyone here, if you've got any questions, you want to know more, please speak to us on the forum. It's just a bit easier to have technical discussions on the forums than it is in the YouTube chat. So yeah, really thanks for everyone for watching. Thanks for your time. Please speak to us about what you're doing with robots. We'd love to see what people are making. And yeah, we look forward to increasing the functionality that we've got so far and making robots as common a place as milling machines. I know Alex would be happy with that.
Thanks everyone.
Cheers, everyone.
Thanks, Richard.
See you soon. Bye.